Hello everyone. So in today's lecture in this topic we'll start about the transport phenomena. Now what do we mean by transport phenomena? So as the name suggests, transport phenomena means it is the transport of certain quantities. For example, the certain quantity can be, say, for example, heat, or say just a mass, and all these things we can actually have, or we can formulate under a generalized formulation that we are going to discuss. Now when we talk about transport, it can be transport through gas, or in a gaseous medium, or transport through liquid, which means actually transport inherently involves a fluid medium. Now because the fluid actually flows, and then we talk about the generalized transport equation, where transport of something, again the something can be heat or something can be a mass, actually flows due to gradient of some other quantity. For example, if you have a temperature gradient, like you have a variation of temperature, then you will have a flow of heat. Similarly, if you have a concentration gradient, then actually you will have a flow of mass. And these are very obvious, like why things flow if I have a temperature gradient. But so we are not going to discuss the microscopic way how it is happening. We'll give some picture, but what we are going to do is a rather phenomenological approach, in the sense we know that there is a gradient of some quantity and something is actually transporting or being transported across this gradient. Now how do you approach this problem? Now think about a very simple problem, that I have a tube and some water is suppose flowing through this tube, or suppose instead of water, let us think about I have a pipe and then some gas is flowing, and the gas is flowing from, say, due to the pressure difference, where I have a P high and P low, something like that. So the pressure on this right hand side is low than the left hand side, and that's why the gas is flowing from left to right. Now in this case I can actually define a quantity which is some transport quantity, and I will call it as in general J. Now J is known as flux. I mean, we will connect it later, and why it is called as flux and what is the importance of flux, how you can derive it. Now this J is this transport of this quantity, the flux. It can be again flux of heat, it can be flux of mass, something like that. And in general, flux means the quantity being transported per unit area, per unit time, and that I am saying will be proportional to some, in this case actually it is proportional to the gradient in the pressure. Now if everything is one dimensional, I can just write it. This is nothing but the pressure gradient as a function of z. So if this is the z direction, so that's why I am writing suffix z. So transport of along z, or the flux along z of that quantity is proportional to the pressure gradient along z, and we then write the proportionality constant as c, which will define later what is this constant and how will you evaluate this constant. Now as you can see that in this equation, the pressure gradient in the positive z direction is negative, because pressure is higher here and pressure is lower here. So usually the whichever quantity you are talking about, either it is a mass or it's a heat, that flow from the high temperature gradient or high concentration gradient to the low concentration gradient or low temperature gradient, something like that. So if we plot the gradient, if the gradient is linear, for example, if we had plotted pressure versus z, I will see if I am increasing the z, the pressure is falling. Of course, it is an oversimplification, because I have written it as the gradient is a linear function, but whatever it is, I see it's a negative quantity, the slope is equal to the gradient, which means actually then by definition the flux will be negative by our mathematical formulation, but by definition the flux cannot be negative. So in order to keep the formulation consistent, what we do is that we introduce a negative sign here, so that this constant also is positive. My left hand side, the flux is also positive, and dp dz is negative, but if I take negative of dp dz, that is positive. So this will be our general formulation. Now, although flux, the way we have written it is a scalar, but strictly speaking, actually it's a vector quantity, and because it's a transport in a particular direction, and truly speaking, if you want to write it properly in vector notation, we have to consider the gradient of pressure, where actually this gradient is nothing but the spatial gradient, which is itself is a vector I del x plus j del y plus k del z of p, where this I, j, k are the unit vectors along the three Cartesian coordinates. But we will be using only very simple notation, in the sense that we will be just restricting ourselves as if it is an one-dimensional gradient and everything is flowing in a particular direction. Now, next thing, so this equation is known as Poiseuille's equation, and the next thing we are going to understand is what is this flux, in the sense that whatever we have told so far, that there is some quantity called flux, and this flux, as we have denoted it as flux, in this case actually we are talking only along flux along z direction, which we wrote as j suffix z. Now, this has, as we said, that it has a molecular origin, although again we are not using any explicit nature of the molecules. We will be using it very classically in the sense, and we are only doing it phenomenologically. And we are just describing the phenomena. If the molecules move, how the flux will, what will be the mathematical expression for the flux. Now, suppose I have some arbitrary surface in my system, and all I want to calculate is how many molecules is crossing this surface per unit area per unit time, because that quantity is related to the flux. Now, also all we want to do is that we want a jet projection of that quantity, because we are only considering the flux along z axis or z axis. Now, let us draw a picture. So, what we are saying here, suppose we have some surface, suppose this is the particular area that we are considering, and let us say that the cross sectional area of this particular shaded region is A, and this is the positive z axis, this is my coordinate system, and then of course I have actually this three-dimensional coordinate system. I am only considering the flow along z axis, and suppose some molecule is coming at some angle and hitting this surface, hitting this side. Suppose this molecule has a speed of say v. Okay. Now, the question we are asking is that how many molecules are going to pass through this surface per unit area per unit time. In order to understand that, let us suppose that the molecule or set of molecules have speed say v in this direction, which are striking this area and which are coming from top. Now, we can say that what is the say in time delta t, how many molecules will actually with velocity v will strike this particular area. So, this is very simple to calculate, because we can always say that the molecules which are within the distance of v into delta t, so they will come and hit this surface, because v is my speed and delta t is the time. Speed into time interval is nothing but the distance traveled. So, those molecules which are actually lying within this cylinder, which cylinder? This cylinder, and has a speed in that direction, and the magnitude of the speed is v, will actually come and strike this particular shaded region, which has a cross section of A. So, this is as simple as that. So then I can also calculate the total number of molecules, because I have to calculate the total number of molecules passing through this area per unit time per unit. Again, we will divide by the area to get the per unit area concept. So in time delta t, molecules with speed v, okay, say hit the shaded area. That was our starting point. And then, which means the number of molecules which are basically we want to calculate the number of molecules that strike this shaded area. That will be nothing but whatever are the molecules, those molecules which are basically lying within this cylinder. So how do I calculate it? I have to calculate the volume of the cylinder and times the density of the molecule. So how to calculate the volume of the cylinder? Now see that this cylinder is a slant cylinder. It has something like this. It has a cross-sectional area. The base area is A, and it has a slant like this, something like this. Now let us assume the cylinder has this axis, and this axis is making an angle theta with respect to the positive z axis. So in our spherical polar coordinate concept, so this is nothing but the azimuthal line, which is the inclination with respect to the positive z axis. So the vertical height of the cylinder we can easily calculate. If the distance is v into delta t, the vertical height will be v into delta t into cosine theta. So the volume of the cylinder v times the density of the molecules, that will be nothing but v times n star. Let me actually replace the v first. So v is nothing but now the base area times the vertical distance, and the vertical distance, as we just said, it is v delta t into cos theta. Let me write that n star first. So I will write n star times, instead of v I am writing small v, which is the velocity. This v is the volume, capital V, v delta t into cos theta. Now this is basically the height times the base area will be the volume. So this quantity is volume of the slant cylinder. Now all we are interested is not the number of molecules that strike this shaded area, but we want to calculate a quantity which is per unit time and basically per unit area. So that can be easily figured out. So we just have to divide it by area times the time it took. So it has to be divided by A times delta t. So I'll just get these arbitrary things cancelled, and all I'll be left with is nothing but n star into v into cos theta. Now we have a situation here. We actually assumed that all the molecules which are coming have a very unique speed, which is v. Now that is not correct, because we know that at any time for a gas molecule, let us assume that this is a gas molecule we are talking about, we will have a Maxwell-Boltzmann distribution of speeds. And not only that, these molecules, the speed, of course we have a speed distribution, but think about it, these molecules are also coming from different direction, because we just took a particular region, particular angle, at angle theta, it is inclining with respect to the positive z axis, but there could be actually other angles. So we have to consider those angular distribution also. So what we are right now saying is that we just told that some set of molecules which are lying within the distance v into delta t, and for those molecules I calculate the number of molecules which have that condition, which have velocity v, and how many of them are crossing per unit area, per unit time. That's what we have calculated so far. But then, as I said, the molecules will have a distribution of speed, and secondly, these molecules are also coming at different directions. They can come from here also, they can come from here, and not only that, so the inclination angle will be very, very different. And not only that, as you can see, the molecule can come from a same angle but from a very, very different direction, in the sense that their projection on this xy plane, that angle is also going to change. So we have to actually integrate over these two angles also. So what we are going to do right now is to make a more general form, in the sense that I am saying that I am going to calculate some flux which is, let's say, from theta to d theta, if we vary the angle a little bit, as well as the other angle phi to phi plus d phi. And if I have a velocity distribution, if I go to v to v plus dv, what will be the quantity? Now already you know that this from theta to theta plus d theta and phi to phi plus d phi, if we rotate our vector, then we generate a cross section area, and we know that from the knowledge of our spherical polar coordinate system, that this area comes out to be sine theta d theta d phi, and with a r squared thing, but then actually there is nothing called r, it's actually a velocity space we are talking about. So this volume will be basically v square into this. And if you want to take a distribution of molecular speed, so that means actually you have to multiply the entire thing by the Maxwell-Boltzmann distribution of molecular speed. Now we have a problem here, because if you remember, when we write the Maxwell-Boltzmann distribution for molecular speed, we write basically 4 pi into some constant, which is m by 2 pi kbt. You can actually go back and check this Maxwell-Boltzmann distribution, e to the power minus m v square by twice kbt into v square dv. So it basically says what is the fraction of molecules, or what is the probability of molecules of having speed in the range v to v plus dv. Now when you say speed, it is independent of the direction. But now actually we are going to use the Maxwell-Boltzmann distribution, but we are again imposing the condition that there is a directionality. Now if you remember, if you have studied this thing, how this 4 pi factor comes, you will readily realize that when you derive the Maxwell-Boltzmann distribution, we first considered a velocity distribution, like say velocity for Vx or something like that. What will be the probability for Vx to Vx plus dvx? And that we got something like some constant into e to the power minus some constant into vx square, something like that. So then what one does is that then we consider the isotropic nature of the gas molecules, and then we say that the y distribution will also be something like this, and similarly for the z distribution also. So together then we see that if we take the multiplication, because we know that the x component distribution and the y component distribution and the z component distribution, these are also probability distribution, and since the distribution in any direction is independent of the other direction, we take the total distribution as a multiplicative thing, and then we just simply do this multiplication, vx dvx into vy into dvz, then all this individual distribution give you something like a cube e to the power minus b, and then all these exponential terms will actually add up, because exponential a plus into exponential b into exponential c is nothing but exponential a plus b plus c, and that way vx square plus by square plus bz square give you v square, and then you are left with some volume element which is dvx, dvy, dvz, and then in the next step you integrate this volume element, in the sense that you say that all I want to calculate is a speed distribution independent of the direction, and that you calculate from this quantity which you just wrote here, but you integrate now over all the spherical polar angle in the velocity space. Now what we are right now doing, we are doing a trick here. We are saying that, so let me just write it what you had done. So we take theta from 0 to pi by 2, phi from 0 to pi, and then integrate this function into dvx, dvy, dvz, and instead of dvx, dvy, dvz, we use the spherical polar volume, which is v square sin theta d theta d phi. And this differential volume now integrate, and if you integrate it, you can easily see that integration of sin theta d theta over 0 to 2 pi will give you 2, and integration of a d phi over 0 to 2 pi will give you 2 pi, and this gives you this 4 pi factor. Now we do not want to introduce exactly or use exactly the Maxwell-Boltzmann distribution here, because the Maxwell-Boltzmann distribution is already integrated for the different angles. It is a speed distribution. So we want a similar distribution up to here, in the sense that we want, we'll integrate it once again. So we want a speed distribution which is dependent on the direction, and then we'll further integrate just like we did for the Maxwell-Boltzmann distribution. So long story short, what we are going to do is we are going to actually multiply it by a distribution function for this velocity, but which is not actually Maxwell-Boltzmann distribution, but rather which is Maxwell-Boltzmann distribution divided by the 4 pi factor. Because this 4 pi factor comes after you integrate over the all possible variations. Because if I write it, that will be our original Maxwell-Boltzmann distribution, as you can see. So this divided by 4 pi is nothing but our original multiplication of the distribution functions along 3 different directions, where we kept the volume element as dependent on theta and phi. So long story short, what we are going to do here, we have already seen an expression for the flux along z, and what we are going to do is that we are going to take this flux, multiply it by the spherical polar volume element. If I go change it from v to v plus dv, r to r plus dr, that way, and then what we will get, we get a surface element, a differential surface element, which you obtain from going from theta to theta plus d theta and phi to phi plus d phi, and that will be equal to something like v square sin theta d theta d phi, and plus we are going to have one Maxwell-Boltzmann distribution. So together now we are going to add these two things, and we are going to see actually what we are going to get with this. But please don't forget that we already have a v sitting here. So if you do it carefully, so then what we are going to get, and remember this Maxwell-Boltzmann distribution, what I just said, if I change theta to theta plus d theta and phi plus d phi, and as well as change v to v plus dv. So v plus to v plus dv means there will be a distribution function, but then I will not take the distribution, there is a v square in the distribution function, because if you remember that we will get this 4 pi v square term after the integration of theta and phi. So what we have to do is that division by 4 pi v square. So I have to take only this part of the Maxwell-Boltzmann distribution. So like m by 2 pi kbt whole to the power 3 by 2 e to the power minus mv square into dv. But I don't need to write it, because we will see that why you don't need to write it. So let us first try to draw the coordinate system which we just discussed. So we are talking in terms of the spherical polar coordinate system. And first we calculated the number of molecules which are coming in a particular direction. Now particular direction means it had a particular inclination angle which was theta, and it also has a particular angle phi, but we do not want these molecules coming in this particular angle. We want to actually have molecules coming from all different angles, and for that you have to calculate. Suppose I am saying that okay, molecules are coming let's say from all different angles. So how do I do that? So I have to vary the angles. Suppose I change this theta to theta plus d theta. It's a small angular increment, and this is basically the small angle is d theta. Let me just draw it more clearly. So this is theta, and this is theta plus d theta. And similarly, I can also sweep another angle from phi to say phi plus d phi. So let's say this is the phi to phi plus d phi angle. So together, what we are going to see here is that we will actually sweep an area going from theta to theta plus d theta and phi to phi plus d phi, and this area is v square sine theta d theta d phi. So that is the area. But then what I am saying here, my speed is also varying, meaning this axis, if you remember, what we had is the distance, and this distance is nothing but v into delta t. Now that is also varying. Now I am saying that I will also vary v to v plus dv. So if I do that, then I just have to multiply it by dv, and then I'll get a differential volume element the way I have drawn it, and that will be just multiplication by dv. In this case it is dv into delta t, but we are dividing it by delta t at the end of the day, so it doesn't matter really. So what we have is this quantity. Now the same way we also derived the Maxwell-Boltzmann distribution, and then what we did, we just integrated over the sine theta d theta, but we will not integrate it first and then again use the values. We will first use the probability distribution in the general form, because our flux also depends on the angle and all this distribution. So we will use the distribution where actually all these things are present, times I have to also include the speed distribution, which is fv to fv plus dv, but keeping in mind that we can actually associate the dv like here, because we are considering a range of speed, but we have to divide by 4 pi v square, because that was the total volume after the integration. So this is basically my distribution function, and that is a probability function, and that we are now going to multiply with whatever we got for a single speed in a single in a unit direction. And that was, if you remember, that was something like n star into v into cos theta. So we just do it, we just multiply it by n star into v into cos theta, and then we will integrate it. Now, so integrate it for what? It will integrate it for theta, phi and v. Again, theta is this angle, and as you can see that theta is going from all possible angles. Similarly, phi is also going from all possible angles. Now what we can do here, we can play a trick here. Now let us have a look here what we have just derived. Now you can see that I have, for this v square and this v square will cancel. So I have the Maxwell-Boltzmann distribution. So for the v integral, it is nothing but v into fv dv, and the integral of v between, and the range of speed is basically 0 to infinity, and then there is a 1 over 4 pi. Now this is nothing but the expression for the average velocity, average speed, sorry. So we'll write it as average speed divided by 4 pi. We don't need to actually explicitly use the Maxwell-Boltzmann distribution. And then what we are left with, this d phi. That's a straightforward integration between the limits 0 and 2 pi. And then we are left with the theta integration. We have sine theta d theta plus we have a cos theta, and this cos theta is coming because we had a generalized formulation where actually the cylinder was a slant cylinder for an arbitrary molecule coming with an angle theta. So that's why we'll have here sine theta cos theta d theta, and that integration is between 0 and pi. Now I did not tell this, so you can think about it. This integration will not be between 0 and pi. Why? Because what I am saying is basically a flux. Now flux has a direction. Now you can think that my entire coordinate system, in the xy plane, I have an xy plane here. This is the z axis, and suppose this xy plane actually divides the system into two halves. Okay, and then I am considering the flux, which is the net downward flux. So I don't need to consider the flux which is coming from the bottom. So you can think about it, this is a sphere and I have divided the sphere into two halves by the xy plane. So I have two hemispheres. Now I am only considering the molecules which are coming from the top and crossing this thing, because flux has a directionality. So I am talking about crossing the surface which is lying along the xy plane. So I am talking about directionality for flux along crossing the plane. Now you might argue that there will be also molecules coming from the bottom. We will do it later. First we are considering the net downward flux, and for this actually the way we will integrate it, we will just integrate it from 0 to pi by 2, because for a hemisphere, if you remember, my inclination angle will be just up to the xy plane. So this angle, the maximum angle is pi by 2, not pi. So that's why we did not use the Maxwell-Boltzmann integrated Maxwell-Boltzmann distribution. We just used up to the point before the integration, which gives us this 4 pi v square. That's basically the surface area of the sphere of radius v. So that part we did not do because we will integrate over the hemisphere, but we took the probability distribution in the most general way that depends up to on theta and phi. And that part is nothing but 4 8v dv divided by 4 pi v square by simple argument, and then we used it. And this phi integration readily gives you the 2 pi, and this integration, now you can think about it. What is this? This is sine theta cos theta d theta. Now cos theta d theta is nothing but d of sine theta. So this integration is also very easy. So it is just integration of sine theta and d of sine theta. It is x dx kind of integration. So the integrand is x square by 2. In this case, it is sine square by 2. Now sine square evaluated between pi by 2 and 0. Sine pi by 2 is 1. So sine square pi by 2 is also 1, and sine 0 is 0. So 1 minus 0 is 1. And the integrand was, remember, it was 1 by 2 because it is x square by 2. So we will get a half factor here. So what we will get is nothing but we will get one half factor, and then if you see here, this 2 and 2 cancels, these pi and pi cancels. So what we will get is 1/4. We had an n star also here. I did not write it, so I will have a n star over 4 pi, this n star, and I will have a n star into v. So I will have 1/4 n star into average velocity. So this is basically the expression for my flux up to this point, but this flux is the net downward flux. So I can actually write a minus sign for that because it's just the flux describing the downward thing. So up to this, I have somewhat general expression for the flux. Now let us quickly check what is the dimensionality, in the sense that what we just got is the flux is connected to n star. 1/4 is a number. So n star is a density. If you remember that we just calculated the total number of molecules by taking the volume of the cylinder multiplied by the density. Now density means per unit volume, so 1 over centimeter cube or 1 over meter cube. So let us use actually the meter cube notation. So it will have something. So it is basically number of molecules times meter cube. That is the dimension of n star. And what is average velocity? It is just a velocity, and average velocity will be meter per second kind of thing. So together what we are getting, the dimension is number of molecules or number of particles in some cases times you will have meter to the power minus 2 and second to the power minus 1. So which is nothing but number of molecules per unit square area per unit time. So that's what was the definition of the flux, and it is not surprising that we got the correct definition. Secondly, this average velocity which we wrote here, you know the expression for the average velocity, it is 8 kbt by pi m for using Maxwell-Boltzmann distribution. Now we will see that we will just make this expression we will just make it more and more correct, because as you see that we did not calculate here the net, there are also downward flux, but then we have to consider that the molecules are coming from top, molecules are coming from bottom also, but is there any net flux across the surface? Now for an isotropic system, like suppose I have a chamber, I have a container and I have a gas which is in perfect equilibrium. Now if you consider any plane, you will see the net downward flux and net upward flux are same. So in that case it will be 0. But if there is any concentration gradient or pressure gradient along the z-axis, then the flux will be very different, and in that case actually you can have a net flux going in a particular direction. That we are going to right now calculate. Now in order to do that, we need to understand, we need to actually model the system, and we can model the system as if that the system, I have different planes and I am considering flux along a particular plane. That is the way we did it, like the xy plane, and we are considering this plane. Now we will consider along z axis, which is our axis of choice, along which axis we are calculating the flux. We will first say that let us think that along z axis I have multiple layers, and I will just choose one particular layer and consider the flux across that layer. So let us now proceed.